So, um, here's the current list of assignments. Tonight is due 2.6, the written assignment, and then the web assigned assignment um, for 2.5 and 2.6. And then uh, this line here represents the end of material for exam 2. And this assignment will be on exam 3. But, we're going to move on as soon as we're ready. So the second exam will be on Tuesday next week. So that's the 29th. Covering 1.6 to 1.8, 2.1 to 2.8. And I think that Monday we can, spend part or the whole period reviewing. So on Monday, 6/28, we'll review for exam 2. So you will ask questions. I will answer. Okay, so come prepared with questions. So, if there's a few problems that, from the homework that you're just not understanding, and you want to go over that, or some small part of it, or whatever, you want to go over it, whatever it might be, come prepared with questions. Specific questions. All right, so let's use that time to do review, and then we'll have the exam on Tuesday, and I'll post an assignment for 3.1 after class, but that's not going to be the material for exam 2. That's for the next exam. Right. Okay. So yesterday, trying to remember, did we go over 2.7? Yeah, we did. We went over questions in 2.7, composition of functions and such. So we left off in talking about section 2.8. So let's continue with that discussion, finish that up, and then let's look at some problems in 2.8. So we started out by talking about one-to-one functions. So a function f is 1-to-1 when every range value comes from exactly one domain value. So this function y equals x minus 1 squared, or x squared minus 2x plus 1, is not 1-to-1. Because this range value, remember the range values for the function are on the y-axis, domain values on the x-axis. The range value 4 comes from two domain values, -1 and 3. Essentially what the problem is you've got horizontal lines crossing the graph of the function more than once. The horizontal lines correspond to range values, so there's the range value y equal to 4. And the intersection points tell you which domain values go to those range values. Okay, so the graph of a one-to-one function is said to pass the horizontal line test. Okay, that is, every horizontal line uh, in the range. For every range value, every horizontal line representing that range value intersects the graph once. Or, if you want to say it without this range business, every horizontal line intersects the graph at most one time. So, a function that's a line, a linear function, y equals mx plus b, as long as the slope is not 0, that's one-to-one, right? Because you got this slanted line, and you take a horizontal line, and the two lines intersect once. Y equals square root x, right? Every horizontal line intersects that at most once. Y equals 1 over x. So this is another sort of standard function. Graph, standard function, graph of a standard function to think about. So it looks like that. And we'll talk more about what are known as rational functions, graphs of rational functions. But anyway, every horizontal line intersects it at most once. As a matter of fact, exactly once. The only horizontal line that misses it is just this one here, the x-axis itself. Another observation, a function f of x that is always increasing or always decreasing must pass the horizontal line test and therefore is one-to-one. Right, this function here, y equals x to the third minus x. Sometimes it increases, sometimes it decreases, and as you can see, it does not pass the horizontal line test. You know, horizontal lines intersect up to 3 times. This horizontal line intersects 3 times. This horizontal line intersects twice, so on and so forth. Right? I mean, if you're going to intersect a horizontal line more than once in your continuous function, I mean, you're going to have to increase past and then decrease past at some point. So, essentially, always increasing and always decreasing will give you a one-to-one function. Not necessarily the other way around. That one-to-one always has to be that. And we'll see examples of such later. Now, if you have a function that's not one-to-one, the one thing that you can do is restrict its domain in some way that makes sense, so that it is one-to-one. So, you know, we were talking about this f of t equals t squared, and the domain is all real numbers. That's just the basic parabola, y equals t squared, where this is the t-axis and that's the y-axis. And, you know, I mean, if t represents some real thing, like time in seconds, you know, you probably have a starting time, time 0. So you're only considering the parabola for t greater than 0, in which case you're just getting that part of it. And now it's one-to-one. That passes the horizontal line test because you're not considering the parts where t is negative. All right. Inverse functions. When a function f is one-to-one, naturally or via a restricted domain or whatever the case might be, when you have a one-to-one function, it has what's called an inverse function, which is denoted by this, f to the negative 1 x. This doesn't mean 1 over f of x. It means inverse function. So this is a great example of the shortcomings of mathematical notation, is that we use the same notation to mean 2 different things. Typically, if you mean 1 over f of x, you would write it like this, f of x parentheses to the negative 1 or something like that. If you put the negative 1 here, it means inverse function. Not the best notation, but that's traditional. So the inverse function does the following. If f of a is equal to b, then f inverse of b goes back to a. So this definition only makes sense if the function is one-to-one. Otherwise, you get the following problem. If f of a is b and f of c is b, and a and c are not the same, well, what are you supposed to make f inverse? Is it going to be a, or is it going to f inverse of b? Is it going to be a or going to be c? Well, you know, there's no real reason to pick one over the other. No one is more special than the other. So, this definition needs, a one-to-one function. So, for example, here's a function. So let's have a domain, and let's have a range, and the function is going to be one-to-one. So when you draw these bubble diagrams, a one-to-one function is kind of boring. It just does like this. So this is 1, 2, 3, 4, and this is, what should we make it? 5, 6, 7, 8, something like that. All right, so in this case, f of 1 is 5, f of 2 is 6, f of 3 is 7, f of 4 is 8. And so the inverse, f inverse of 5 is 1. F inverse of 6 is 2. F inverse of 7 is 3. And F inverse of 8 is 4. Okay, so it just reverses the arrows of F. Now, a special property of inverse functions is the following. So the definition of an inverse function which was this: if f of a is equal to b, then f inverse of b equals a, okay, implies the following two properties. The inverse of f inverse is f. So f inverse is the inverse of f, but the inverse of f inverse is f back again. And 2, when you do the composition, one way or the other, you just get the function x, just the identity function x. All right, so the composition just gives you this identity function back, and you can do the composition either way: f following f inverse or f inverse following f, and the composition will just be the identity function. So, for example, consider the one-to-one function f of x equal to x squared for x bigger than or equal to 0. Right, x squared was not one-to-one. Okay, but we're going to restrict the domain. So for the restricted domain, oh, did I start this? I did. X bigger than or equal to 0. Okay, what's going to be the reverse function for x squared? What would be the inverse? Right, I mean, if a goes to a squared, what takes a squared back to a?
Square root.
Yeah, square root. Right, so you see why you have to restrict the domain, because, as I was saying before, right, the square root of x, the square root of x squared isn't equal to just x. It's equal to the absolute value of x. But, if x is just positive, then the square root of x squared is x. If you know that x is positive or not negative, right? But, if you don't know that x is positive or negative, you don't know how to assign the inverse. Anyway, so in this case, it's just the square root of x. All right, and we see that the composition satisfies the required property so f of f inverse of x, well, that's f of f inverse of x, right? F inverse of x is square root of x, right? And f of x is x squared. So f of the square root of x is square root of x squared, which is just x. And f inverse following f of x is equal to, so it's f inverse of f of x, which is f inverse of, well, f of x is x squared. F inverse is square root. So this is the square root of x squared, which is, again, the absolute value of x, but that's just equal to x because we know that x is bigger than or equal to 0. So the absolute value of x is just x, right? If x was negative, what's the absolute value of x? So we're on the same page again. Right? If x is negative, then the absolute value of x is equal to what? How do you express that algebraically? It's minus x. Right? The absolute value of negative 3 is the negative of negative 3, which is 3. Right? I mean, if you just want to go from here to here, you could just say to yourself, I'll just erase the negative sign. Sure, that's fine. But the negative sign is kind of hidden inside the x. If I insist that x is less than 0 and just call it x, then, you don't see that negative sign. So you actually have to negate it. You negate the x to get rid of it, that negative sign on the inside. All right. What about the graphs? What do the graphs look like? So let's look at the graphs y equals x squared and y equals square root x. Let's graph them on the same set of coordinate axes. Again, we're doing it just for x is bigger than 0. So if this is y equal to x squared, if you take that parabola, now this is how you take the graph of a function and then get the graph of the inverse function. It's via a certain symmetry. What you're going to do is you're going to reflect this around the diagonal line y equals x. So here, let's see, how do we do that? First we're going to flip like this. Then I'm going to flip like that. Oops, that's wrong. All right, first flip horizontally, and then flip vertically. Oh no, that doesn't work, does it? And then rotate. All right, rotate 90 degrees. There it is. That's the square root of x. So this is y equals x squared. This is y equals the square root of x. Let's make that, we'll leave that as black. And then in between that, right here, this is the line y equals x right here. And that's the relationship in general between the graph of a function and its inverse. And this is the point 1, 1 right here where they meet. And, you know, they have to meet where x is equal to y because f takes a to b and then f inverse takes b back to a. So the two graphs meet where f inverse of x is actually equal to x along the line y equals x. The graph so in general, the graph y equals f inverse of x and y equals the graphs y equals f of x and y equals f inverse of x are related by reflection around the line y equals x. So that's the diagonal line whose slope is 45 degrees and goes through the origin. So, I mean, if you just picked any other sort of one-to-one function, so let's look at that function y equals 1 over x. Very good. So, well, y equals 1 over x, and then here's the line. Again, that 45-degree line, y equals x. What happens if I reflect that? Now, the picture I drew doesn't really show it. Let me see if I can make it show it better. Okay, better. So you'll notice that the graph of this function, y equals 1 over x, for the restricted domain, x is bigger than 0. It doesn't matter. I mean, you could use the whole thing over the whole domain, all real numbers except x equals 0. But on this restricted domain, you'll see that it's symmetric. If I reflect it around that diagonal line, I get the same thing back. Okay, so notice that the graph obtained by reflection around the line y equals x is the same graph. Thus, f of x equal to 1 over x is its own inverse. Thus, f of x equal to 1 over x is its own inverse. That is, f inverse of x is again 1 over x. And we see that the composition of the two functions gives you the identity function. F of f inverse of x is f of f inverse of x. Is f of, well, f inverse is 1 over x, but f of 1 over x is 1 over x. This is 1 over x, which is just x. Right, it's the numerator times the reciprocal of the denominator. but that's all just x. Same thing the other way around. Because the functions are the same, obviously, it's going to be the same exact calculation, and therefore you get x again. Okay, so generally speaking, to get the inverse function, you just do the reflection around this line. Or sorry, to get the graph of the inverse function, you just take the reflection around this line, y equals x. Right? Sometimes, usually you get a different function, of course. Here's y equals x squared. Here's y equals square root x. But, you know, this one nifty example, you know, you see that you get your own function back as an inverse. Anyone see a different function that's symmetric around that line? Linear function, can you think of a line? Linear function that would be symmetric around that line? Y equals x?
Y equals x?
Oh, yeah, of course, sure. Y equals x. Another one? Anyone? Well, anything that's going to be like perpendicular to that, right? If it's perpendicular to the line y equals x, this linear function, this is the linear function like x plus y equals 1. So y equals 1 minus x. That's its own inverse as well. So interesting examples. All right. So what about other functions? How do you find inverse functions? Algebraically. So given a one-to-one function, y equals f of x, if you can solve algebraically for x in terms of y, then the resulting expression for y the resulting algebraic expression will be the inverse function. Right, because you know f of x takes x to y. So then if you can solve for x in terms of y, you'll know how to take y back to x. So that's the basic idea. And you know, this is a few examples. Now, as we were talking, linear functions are always one-to-one. So they always have inverse functions. So if you have y, so f of x is equal to 3x plus 7. Okay? So f of x is 3x plus 7. Let's find the inverse. Right? Well, you start with the equation y equals 3x plus 7, and then you solve for x in terms of y, which you can always do with a linear function. So this is y minus 7 is 3x. And then I can divide by 3 on both sides, and I get 1/3 y minus 7/3 equals x. So this is the inverse function, although usually you like to put it back in terms of x. So f inverse of x, because f is in terms of x, you want to put the inverse back in terms of x. So you, well, let me do an extra step. So now exchange x and y, right? So we're going to have y is equal to 1/3 x minus 7/3 equals y. So now this is f inverse of x. All right, and you can do that with any linear function as long as the slope is not 0. So this works for any linear function. Fx equal to mx plus b, as long as m is not equal to 0. Right, so notice what the slope of the inverse function is. Right, the original function has slope 3. Linear function has slope 3. The inverse function has slope 1/3. Does that mean they're perpendicular? Does that mean they're perpendicular? This has slope 3, this has slope 1/3.
Doesn't it have to be negative 1/3?
Right, exactly. So no, they're not perpendicular. But just in case you were thinking that. No, the perpendicular line, if you have slope of 3, then the perpendicular line has slope. Well, a perpendicular line will have slope negative 1/3. So the inverse function doesn't give you a perpendicular slope. I mean, if you're gonna reflect around this line, like that, well, then you get this. So if this is f, then this would be f inverse. So as you can see, they're not perpendicular. Not that it's impossible for that to, well, no, it is. Isn't it? You could take two, no? Not possible. Anyway, what about other types of functions? Well, this type of function also always has an inverse function. So y equals, now why it is 1-to-1, requires knowing what the graph of this thing looks like, which we really haven't covered yet, but we'll just assume 1-to-1. So assume the function f of x equal to, let's say, x minus, well, let's just do x over x minus 1 is 1-to-1. Find f inverse of x. So I don't know if you remember that example I threw at you guys yesterday of those six functions. When you take the composition of any two of the 6 functions, gives you another one of those 6 functions. This is one of them right here, and the inverse function is again one of those 6. I'm trying to think, is this maybe not the one I want to do? Maybe x minus 1 over x. Yeah, let's do. I think that's the one I want to do. Okay. So let's find f inverse of x. So you write the equation y equals f of x. And you can exchange x and y now and then just solve for y. Why don't we do it that way? So let's exchange x and y first. You don't have to do that step if you don't want to. So x is equal to y minus 1 over x, and now solve for y. You can just solve for y right off the bat, or y minus 1 over y. You can just solve for x right off the bat here. But sometimes folks like to exchange like that. Well, how do you do that with this type of function? Multiply both sides of the equation by the denominator. So I'm going to make yx is equal to y minus 1 over y times y. All right, so these are going to cancel. And I have yx is equal to y minus 1. Now what I want to do is take every term that has a y and put it on one side. All right, so I'm going to subtract y from each side. And what do I get? Let's go over here. Yx minus y is equal to just minus 1. Now I'm going to factor out y, like that, and then divide by x minus 1. So I'm going to have y is equal to minus 1 over x minus 1, or y is equal to 1 over 1 minus x. So that's F inverse. All right, and this will work for any function. This process that I've described here will work for any function of the form. Let me show you. Well, rational function of the form linear polynomial divided by linear polynomial. So this process for finding F inverse of x will work for any function, or rational function, of the form f of x is equal to ax plus b over cx plus d. So such a function, linear polynomial divided by a linear polynomial, well, there's one restriction, where AD minus BC is not 0. So you have to have that. AD minus BC is not equal to 0. So just a technical thing. But this type of function, this is called a Moebius function. Anyone ever heard this guy's name before? Moebius?
Like a Mobius strip?
Yeah, exactly. He's the guy that's famous for the Moebius strip. So that's I mean, he did a lot of other stuff besides that, but this is a Moebius function. All right. What other sort of examples could we do here? Let's look at the book. See what they got for us. Actually, they're all Moebius functions and simple. Well, this is a nice example. Okay, let's do this one. How about number 61? So let f of x be equal to 61. 4 minus x squared for x bigger than or equal to 0. So for x bigger than or equal to 0, 4 minus x squared, it looks like this. So again, it's a parabola. That looks like that. This is 4, and this is 2. Well, actually, it's not a very good 4 and 2. That's better. So this is the function y equals 4 minus x squared. For for x is bigger than 0, and as you can see, it's 1 to 1. Find f inverse of x. Okay, well, you start with y equals 4 minus x squared. If you want, switch the x and the y's. So x is equal to 4 minus y squared, and then solve for y. So what I'm going to do, I'm going to put the y over here. And now I'm going to move the x over here. And now I'm going to take the square root. Right, so the square root of y squared is the absolute value of y is equal to 4 minus x. But you'll notice that the range of this function, the range is equal to minus infinity to 4, right? Which is exactly where the square root of 4 minus x is positive, you know. But since the range of f equal to minus infinity to 4, right? We know that that we're looking at the positive square root. Uh, 4 minus x. So we take y to be the positive value. Well, no, actually, let me think. Yeah, just the positive value. So this is y is equal to 4 minus x square root. So that is the inverse function. Right, so starting with f of x equal to 4 minus x squared, right, we look at the equation y equals 4 minus x squared, switch the x and the y's if you want, and then solve for y. Or just start with this equation and solve for x. And then you have to use a square root at some point, but you typically will take the positive square root value. Okay, another reason why you can think of this as the positive square root value is if you take this graph right here, this is maybe a clearer explanation. And you do the reflection around the line, y equals x. So flip. Rotate. Then you get this picture. So 4, 2, or no, it's going the wrong way, isn't it? Like that. It's not a very good look. There it is. Oh, fix that a little bit. So here's the 4, here's the 2. So here's 4 on the x-axis, 2 on the y-axis, and here is the line y equals x. Right, so this is the original function, y equals 4 minus x squared, and this is the inverse function, y equals square root 4 minus x. So at this step right here, are we going to take y to be the positive of the square root of 4 minus x, or are we going to take y to be the negative of the square root of 4 minus x? Well, geometrically, right, when you do this reflection, you see that the y value is always going to be positive. The graph is not down here when you do that reflection. Okay, so the inverse function should be the positive square root 4 minus x rather than negative square root 4 minus x, so that it gives you this, this picture that you're looking for. The negative one would be down here. Okay, so that's all the material in section 2.8. So on Monday, we will go over a few more problems in 2.8, and we're going to review. So come prepared with questions on Monday, specific questions. I'd like to go over number 65 in section 2.8, or I'd like to go over number 22 in section 2.1, or all the way back to section 1.6, 1.7, 1.8, all the way from 2.1 to 2.8. And I'm often getting questions like, what problems can I expect? Again, the written problems that you handed in, those are the problems that are very similar to what will be on the exam. Okay? The written homeworks that you handed in, stuff that's similar to those, that's what's going to be on the exam. So, like, I asked you to hand in section 2.6, numbers, well, not 2.6, in section 2.7, 16 and 56. All right, so number 56, if we look at it in 2.7, you got a function f of x and a function g of x, and you got to find the compositions. F following g, g following f following f, and g following g. All right, so since I assigned number 56, stuff similar to that would be like number 55 and number 57. Okay, so those are the things you need to look at. So you need to understand number 56, and you need to understand the problems around it. 54, 55, 57, 58. Right? That's going to be, good preparation for the exam. And every question I ask will be very similar to those. All right. Moving on, let's start on section 3.1. Is on quadratic functions. So we've talked about linear functions already. A quadratic function is of the form f of x equal to ax squared plus bx plus c. So, that is a polynomial of degree 2. So a quadratic polynomial. I can't stand the word quadratic because quad is 4, and yet it's got degree 2. But it's tradition, so what are you going to do? Can't buck it. The standard form for a quadratic function is like this. So just like with circles having a standard form, a quadratic and linear functions having a standard form for a quadratic function is as follows. F of x is a times x minus h squared plus k. And, this is a standard transformation from this is the transformation, all those transformations we talked about in section 2.6, from the standard parabolic function f of x equal to x squared. So the graph y equals a times x minus h squared plus k is obtained from the standard parabola y equals x squared by the transformations from section 2.6. So, for example, sketch the graph. Sketch the graphs of y equals x squared, y equals x minus 2 squared plus 3, and y equals x minus 2 squared plus 3, and y equals minus 4 x minus 2 squared. Let's put a half plus 3. Okay, so let's start with y equals x squared. Actually, let me do one more even. Oops. So we're going to do all these functions. We're going to start with the basic parabola, and then we're going to do all of the variations of it using those transformations from section 2.6. So we got x-axis, y-axis. I'm going to be very careful in my drawing here. Here's the right-hand half of the parabola. Let's do the reflection and stick it here. Okay. All right. So this one, x minus 2 squared plus 3, you start with y equals x squared. So that one will be black. And we're going to shift it 2 units to the right, 3 units up. So 2 units to the right and 3 units up. Well, actually, let's see. This needs to be skinnier, perhaps. Yeah. So that's the standard one, y equals x squared. So now y equals x minus 2 squared plus 3 is obtained from that by shifting to the right 2 units and up 3 units. So 2 and then 3, right about there. Let's make it red. Let's get rid of that. So that was y equals x squared, and the red one is y equals x minus 2 squared plus 3. So this point right here, instead of being 0, 0, you shift right 2 up 3. So this is the point 2, 3. And right down here, of course, is the origin, 0, 0. This one, minus x minus 2 squared plus 3, okay, you're going to, first of all, flip the parabola, and then shift it to the right 2 and up 3. So flip the parabola upside down, because we're negating. That's reflecting around the y-axis. So you go from x squared to minus x squared. So that takes this parabola and flips it around the x-axis, and then move right 2 up 3. So what you get in that case is just this thing reflected upside down. So this is right here. And let's make it blue. So this is y equals minus x minus 2 squared plus 3. So now, what about this one? What's the difference between this one and that one? Well, now the parabola gets squashed by 1/2, right? It gets squashed vertically by a factor of 1/2, right? Because you take the outer function and you multiply it by a number less than 1, right? And it's negative, but we already took part in the negative thing, took that into account. Now it's going to get squashed by a factor of 2. So same function back again. And now I'm going to squish it by 1/2. So right about there. And we'll make it green. So that is y equals minus 1/2 x minus 2 squared plus 3. Okay, so in all these pictures of parabolas, okay, we took the parabola, the standard one, y equals x squared, and we shifted, reflected, and squashed, and stretched, or whatever. But when you have the quadratic function in its standard form, you know more or less what the graph is going to look like. Right? And we saw that the standard form was important before when we were solving quadratic equations. Ax squared plus bx plus c equals 0. Although this, we had to complete the square to do that, although this is going to be slightly different. One thing to notice is that the standard form always tells you where this vertex is. So the vertex of the parabola or quadratic function f of x equal to a times x minus h squared plus k. is at the point x equal to h, y equal to k. So notice this is minus h. So if this is x minus 5, then h is 5. If it's x plus 5, then x plus 5, then this is negative 5. In the k, there is no flip in sign. All right, so that's the point where the parabola turns around. So y equals a times x minus h squared plus k. If a is bigger than 0, if a is less than 0, it's the reflection of that. Come on. Y equals a times x minus h squared plus k if a is less than 0. But in both cases, this is the point h comma k. So for example, the vertex of the quadratic function fx equal to 2x plus 5 squared minus 6 is at minus 5 minus 6. So you flip the sign here, right, in the squared bit. So x plus 5 indicates an x coordinate of minus 5, and the minus 6 is y coordinate minus 6. Right? So so we need to get that straight. So now if you've got a quadratic function that's not in the standard form like that, okay, how do you get it back to the standard form? Well, you do completing the square, although there's definitely a little bit of a twist to it this time around compared to when we were solving quadratic equations. It's got to be done a little bit differently, but we'll cover that later on Monday or on Wednesday. We'll get back to it, okay? All right, so that's all for today. Email me with questions or concerns or if you'd like to meet. And other than that, have a good weekend, all right?